I'm back. You can't stop me. I just keep turning up like a bad penny. Whatever that phrase means. I hope that's a fine phrase to use. Right, so it is still today. I'm doing a twofer today because I wanted to split keyboard stuff from boring let's solder broken wires back together on this keyboard to split up that and actually building hardware to plug this thing into an NES, which is what I'm going to do now. This will be a shortish one. Let's see, it's 7:36 right now. I told my wife I'd knock off about 8 o'clock so that we can eat Chinese food and play Grim Fandango, which I am very much looking forward to. So I intend to stick to that, but maybe about a half an hour stream right here. And we'll just get set up with some stuff. So let me go to the overhead. So just finished this up. Yay! Basically tons of traces that I had cut on this keyboard ages ago, and we wired them back up. And this is currently plugged into a Pi Pico that has a little Python program on it that is just scanning the keyboard matrix to allow me to double check that the keys look like they are more or less registering properly. So that looks okay-ish. But now I am going to get rid of the Pi Pico because we don't need no stinking microcontrollers to get this keyboard interfaced to an NES. We don't. I'm telling you. If we could, I shan't. Let me just throw this in the garbage pile. And let me yank some stuff off here, which someday I will get back to this. So, as you will know if you are tuning back in from the last one, I'm going to VCF Midwest again. I can't believe it's already been a year. It's wild. Last time, well, you'll see, like, basically I made my last set of videos for VCF Midwest and then went radio silent. Promised somebody that I would totally do, promised somebody who commented on my videos that I would totally do a VCF Midwest, like, recap video, and then didn't post anything, I don't think, until I started streaming this crap. So, yeah, yeah. But it's been a year, and I am looking forward to going back regardless of what I have to present, which, you know, I've got some old standbys that watch the stream, one of which is good old Trey Dempsey, who is going to be there, very excited. And he has voted, and of course he gets top votes just by dint of being here, that I attach a floppy drive, regardless of what we actually manage to do with it, to the NES. Should be the goal when we get there. But one thing at a time. First, we have to make this keyboard actually talk to the NES. Right, and I got kind of sidetracked there, reminiscing about VCF Midwest because I was going to tell a small story that was related to this board that I'm almost done cleaning up. When I was at the one last year, I picked up, it's actually behind me, but you can't see it. I can rotate the camera slightly. It will be out of focus, but oh well. Vaguely here. That's Atari ST Mega? Yes, or something. Spent a bunch of money on that because I'm foolish, but I don't have much Atari stuff. And I don't have really any 16-bit stuff, which, like, man... Okay, so I'm 32. I started getting into this crap when I was... I mean, you know, like, 12-ish. When I was a wee lad. And back then, like, everybody was reminiscing on Amigas, and they were still bleeding cheap, and I never bought one, and I never bought one, and I never bought one, and now they are expensive as balls. I think I was saying Amiga that whole time. I hope I was saying Amiga, because anyway, still don't have an Amiga. So the Atari ST is a nice, I don't want to say consolation prize. I'm actually more interested because I like the weird ones. But anyway, what I had on here was I was making my own, it has kind of a SCSI that's not SCSI bus interface on there for hard drives. on the ST Mega, and I was working on making my own interface for that, even though there are solutions for that, but it was just a project I was working on. Anyway, built that for the computer that I bought at the last VCF. So here we are, full circle. Anyway, so let's get the keyboard out of here for a second, actually. And the keyboard may not come back into the picture for a little bit, interestingly, because sure, you can be in this picture and not in that picture. That'll work. Yes, so may not reappear because I mostly need to get set up with the stuff that I'm going to use to build the interfacing hardware between the keyboard and the NES. So, I actually have an NES cable from previous futzing sitting around right here. So this was carefully removed from a real controller and will be returned there someday. But controller is really very, very simple. NES controllers have, and this is if you've been following along this whole time, this is a rehash of a rehash of a rehash. But fundamentally, there is, besides power and ground, there is a wire for latching controller inputs, which basically means, hey, give me exactly what the controller inputs are right now, grab them, hold on to them. And those get grabbed into a shift register, which a shift register is kind of exactly what it sounds like. After it grabs those 8 parallel values from each of the 8 buttons. Is NES controller 8 buttons? I think so. 4 on the D-pad, A and B, and start and select. So that sounds like 8 to me. Anyway, so it clocks in, or it grabs those, saves them in the chip, and then it has one pin that is for serial output, and there's another pin for clock, and every time you toggle that clock pin, it will take those 8 values and shift them down one, and the last one will fall off the end basically on that output pin. And so you've basically got one of these pins is that clock pin, and one of these pins is that data output pin. And so it just clocks that 8 times to get the 8 values, and that's how you get them into the NES, and that is the NES controller port. But it doesn't need to be 8 values, it can be whatever you want. So, for example, if you have a keyboard with 100 switches or whatever it is, an arbitrary number of switches, you could basically just clock in 100 times and then you get your keyboard stuff. Slightly complicated on the hardware side, because to the NES it really you could just implement it in a way, and more or less what I plan on doing will look to the software side like you just have like a 100 button controller or whatever it is. Let's see. It's I'm looking at the keyboard matrix, so it's 8 by 6, I think, which is come on elementary school times tables. Oh my god, what is that? 48? Is that 48? That seems low. But 6 times 4 is 24, right? Oh god, yes. And then 2 times that is 48. Yes, I'm not crazy. I can do elementary school multiplication. Anyway, so apparently it's only 48 keys. Interesting. Actually less, because there are 2 unmarked things on this. But anyway, Derek Koenigsberg says 8 times 6 was always the combination I could never seem to remember. Good. No, seriously, in elementary school, I didn't like fail at times tables, but I don't know, like I don't really remember how bad I did, but like in 4th or 5th grade or whatever, when we had like the big times tables test, I remember it because it was traumatic for some reason. It was like you got for like maybe it was like every row of the times tables that you remembered perfectly, you got a taco. And I was so sad because I only got like a couple tacos. And that stuck with me. Yeah. So, genius I am not. Anyway, so that's how that works. But because of let's get back on track. Because of the matrix nature of the way that keyboards like this work, and in fact, because I'm trying to do some intro for people who are coming into this that don't really know what's going on yet. This is what the keyboard looks like kind of in a circuity way. And this is pretty much how it's done for all keyboards, because it allows you to... why am I looking at my stream screen when I could be looking at my actual desktop? It allows you to use a fewer number of inputs to drive a lot of buttons. And, I mean, yeah, this is a terrible... Let me actually get the website. Maybe not pull up my mail. Here we go. Okay. So you've got 15 pins, but you've got 48-ish buttons, right? And that's because each button lies at the juncture of the connection of 2 pins. And so kind of the rough thing with matrixing anything is you run through the columns, the vertical lines here, turning them each on in turn, and then you check the outputs, the horizontal lines, to see if any of them is on, which would mean that that switch is pressed down for that particular intersection of column and row. And that is the complication with this hardware, is that, you know, I can't just like clock all of these buttons. I can't just latch them all into one giant shift register and then shift them all out. I have to have some hardware that knows how to matrix the keys. Ostensibly, you could do that with, you know, one, like a binary counter and a demultiplexer, which basically a binary counter would count, you know, if you know your binary, it's going to be 0, 1, sorry, I'm going to give you the finger, 2, 3, 4, 5, 6. I'm looking at myself in the camera and it's really not doing me any favors. But it's just, if you don't know binary, which I don't know, well, you know, I shouldn't say if you don't know binary, why are you watching this video? Because I want to be inclusive here, man. If you're just like tuning in because you're like, what is this stuff? Heck yeah, I support you most of all. Anyway, it's just like regular counting, except you are, you know, your numbers are just 0 and 1, and then it rolls over. So 0, 1, it counts 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, all rolls over, 1, 0, 0, 0. So that's a binary counter, is just a chip that does that. You feed it a signal, and every time that signal hits, it's going to count up by 1. And then it will have however many output pins, and they will go, you know, 5 volts. Yeah, let's do it from this side. 5 volts, 5 volts, 5 volts, that's 3, you know, 5 volts, 5 volts, 5 volts. Anyway, corresponding to the counting that I was just doing earlier, each of the pins turns up. And then you could feed that into a demultiplexer, which basically takes that number. It might not be a demultiplexer. I was trying to remember this earlier. I think I'm using that wrong. Anyway, basically just a chip that takes a binary number, like that would be on those counter pins, and turns it into just discrete pins being on or off. So, you know, if it was 0, then the 0 pin would be on, and if it's 1, then the 1 pin would be on. 5 volts, 5 volts. It's off to electricity we go. Derek Koningsberg says, sounds too much like hi-ho. 5 volts, 5 volts. Anyway, so that's how you could do your matrixing, or your scanning through the columns. That would be that side of things. And then really for the row side of things, you could then just more or less use a parallel in serial out shift register, like is actually in the Nintendo controller, to take, you know, you set one of the matrix lines, and then the columns, you latch those values in, and then clock them in to the NES, and that gives you that row of, or that column of keys, and then switch over to the next one, clock them in, read them in. So it's kind of like having, in this case, it's, you know, 7 by 6. So it'd be like having a 7, kind of like having 7 controllers plugged into your NES. but you also have like a smart multi-tap that can cycle between them. Yeah. So that would basically, you'd also need to divide things down because you only want to count across the matrix lines every, I guess, every six. I mean, we could flip this keyboard in the other direction too, because it is 8 columns wide, so that pretty perfectly lines up with a 8 input chip, which is pretty common. Octal chips are pretty common. But I might stick to doing it the other way around for reasons that I will get into later. Anyway, so for every, let's say in this case, every 6 bits clocked in, then you would want to count to the next and assert the next matrix line. So every 6, in my case, which I will get to, which is related to what I was just saying that I would get to, it would be 7. Every 7th bit shifted in to the NES, you'd want to switch to the next matrix line. So here's the thing. There are chips that do that. Obviously, there is the one in the NES for doing the parallel in, serial out. Those exist. There are also chips for doing the counting that I described in the first half. I don't have them. I have many a chip over here in my bin. I'm sorry. I'm getting so off the rails for a stream that I'm like trying to keep to like 30, 45 minutes. But sorry, Zelsa is how I'm going to pronounce it. Sorry. Right in the feed. Randomly saw this on feed. Guy describing keyboard matrix randomly burst into song. Subscribed. This is what I'm shooting for. You know, I'm not aiming to be big. I just want to find the other people that would cop to my style, which is particular. Anyway, okay, so that's the basics of keyboard matrixing, NES input, and how I kind of plan to make those two things jive. But as I was saying, right as I clap into the mic there, I don't have those chips handy. I could order them, but I could also just order a working keyboard. And no, my style is to take old broke-ass shit that I have sitting around and kind of vaguely make it work. I could also use a microcontroller, but I will say for you, Zelsa, because you are just tuning in, part of this whole ridiculousness is that I'm just doing things on my own rules. I'm a bad boy, and I'm playing by my own rules. But my self-imposed rules are for this ridiculousness. They're not hard and fast, but I'm gonna be plugging this keyboard into an NES, and it just feels wrong to use a microcontroller that is orders of magnitude more powerful than the NES to drive the keyboard when it's just simple matrixing, and it's for fun. So building the hardware, building some actual hardware to do it, is the fun part for me. It's about the means, not the end so much. So anyway, don't have those particular chips. What I do have that I bought a while back for something, for building an Apple II card, which actually I still would like to do, but I got these bad boys. These are, as you will be unable to read. Yes, look at that. Beautiful. These are GALs, G-A-Ls. What does it stand for? It's an acronym that really is pretty useless. Something logic. It's basically, I always go with this analogy because I think it's going to be the most accessible. If you don't know what a GAL or a PAL or other programmable logic is, it's like a little tiny FPGA, but super low powered, super low gate count. Basically, you've got 8 or 9 input pins and 8 or 9 output pins on this thing. And then kind of inside of it, you've got this mesh of AND gates and OR gates and inverters that can be kind of, you write to it like a ROM, and that fuses connections together between all of those AND and OR gates inside of it that allow you to generic array logic, Wereworm says, which also, hi, Wereworm and Trey Dempsey. Good to, I mean, obviously Trey was in the last one, so good to have you back, Trey. And Wereworm, I was missing you. Good to see you. But yes, you guys are somewhere in there. Trey says generalized array logic. Wereworm says generic array logic. Probably somewhere in there. It makes sense. Anyway, you can think of it like a tiny, very low-powered FPGA that you can basically, on each pin, you can do an arbitrary logic function, anding, oring, and zoring things together to go from any of the input pins on this thing to have some logical output on one of the output pins. Early PALs were, or PLAs, I think, were the earliest, and they just had the logic part. Then GALs and PALs and GALs. GALs are the most advanced type, which is why the acronyms kind of mean nothing, because they just, like, a GAL is a programmable logic array. So they just changed the first letter and called it a slightly different thing as they added more shit to them. Anyway, it's got registered logic in it, which basically means there's also a D flip-flop on every pin. So if you want to do, you can do not just combinational logic, or combinatorial logic, which is logic that is invariant due to time. You know, it's just like, if both things are and, it'll always be and. Whereas registered logic allows you to remember things. So that's the fun thing about this. So I intend to, since I have these, use these to implement my logic for scanning this keyboard. So for starters, really right now what I'm going to do is, the fun thing is, they are perfectly programmable by the Mini Pro, the TL86, whatever, it doesn't even actually say on it. TL8662 Plus, it says in small text on the back. Can program these just fine, which is super cool. And I have used these in here before, played around with them a bit, so I know it works, but I don't know if I have all the crap on my computer, so that's where I'm going to start here. That's not my computer. That's my computer. So I know I have the programming software on here, but do I have WinKuppel, which is like the official... Yeah, I clearly don't. It's the official Atmel programming package for writing and compiling logic, like images for these chips. And I clearly don't have it installed. So let's install WinKuppel. Why do I keep looking? I am losing my mind. This is what happens when I go on vacation. I keep looking at, like, my monitor, like my like streaming monitor, to see, like, what I'm typing. And my computer is right here. What is wrong with me? Anyway, WinKuppel. Sure. And did Microchip buy Atmel at some point or something? I don't know. These chip companies are always moving and grooving. Is there a download right here somewhere? I have recently downloaded this. It's very easy. It's very easy to do. What? Okay, documentation, sure. Application notes, sure. Where the frick is the download? Hello? Hello? Is it under here? Download WinKuppel. There you go. And it's not open source, but it's kind of supported abandonware at this point. Checking my chat while I install software, which is, of course, one of the most exciting things about this sort of stream. Derek Koningsberg, oh, I lost it, says, last time I heard WinKuppel mentioned was in one of Robert Baruch, sorry, I don't know who that is, Baruch's videos. He always starts interesting projects, gets way far into them, then abandons and moves on to something else, which is what I'm trying not to do, but I can make no promises, because in my personal life I usually do that. But yeah, that is surely a pain. But yeah, WinKuppel is special. Ryan says, yes, a while back, and I do not know what he's referring to. Oh, probably to one of the things I was saying about it being, microchip buying Atmel. Yeah. Which is just funny, because it's, the pick people buying the AVR people. There we go. That's the name of my company. Which is just, it seems blasphemous as someone who is not doing a whole ton, but, playing with microcontrollers back in, like, the early 2000s, because, like, I mean, of course it wasn't, like, that hardcore, but it felt like you either played with AVRs or you played with picks, and it was one or the other. And I feel like AVRs got some real traction because they were, for a while there, were a little easier to program. Like, physically, not like the assembly or the C code. Like, to dump the program into the chips was a little bit easier. I'm going to not restart my computer. Why would I need to restart my computer to run a compiler? I ask you. Motorola 68HC11 for the win. He says, okay, maybe that was bigger in the late 90s. I think that was the one that was in I don't know if you've watched any of my other videos, but the keyboard for my VT420. It was definitely a Motorola microcontroller, but I don't know if it was a HC11. Okay, what am I doing? Win Koople. There we are. Oh, right, I forgot. Oh, and it's right here. Because, again, like, supported abandonware. This program is a bajillion years old. Oh boy, I have way too many windows, and I turned on scaling, so now I don't know where anything is. I guess we can quit Thani. And I guess we can... Well, no, I'm not going to get rid of that. Well, yes, I will get rid of this paint thingy, because I only needed that for remembering what keys I had fixed. And somewhere in here is the WinKuppel video, WinKuppel window that I was just looking at. Here we go. Did they say I needed to enter an organization name? Hopefully not. Alright, it was 6,000, 8,009. And I've lost it again. 6,000, 8,009. And I don't see anything about an organization name, so... Okay, fine. Let's try this again. Oh, missing a 0. There you go. Now you've seen me put in my serial number, probably the most exciting part of the stream. Derek says, I think the HC11 was also super popular for hobbyist robotics, which is a great field for finding endless, unfinishable projects where it's hard to have a sense of accomplishment. Yes, that sounds about right. I'd love to mess around with robotics. Back in my, like, teenage AVR days, I played with steppers a little bit. I was converting a Sears typewriter to like be a teletype-ish situation to make it run serial and drive the steppers and whatnot. And it worked okay, and then I threw it away. And there was a point here. Oh, like that's the, like I used to do more playing with steppers and whatnot, and that was fun. And I miss doing stuff with like physical hardware. I mean, I haven't done it in years and years and years and years, but I still miss it. I always start from the examples, always. And one of the annoying things is when you download WinKuppel, they don't, like, all of these are just kind of for all sorts of different frickin' devices, and they don't really tell you. Like, I mean, they should be compilable to most things, but not really. So, let's see. I think the first bit I need to build, because I have to think about... I'm thinking I'll use two gals, and I will use one for the matrix scanning and one for the like row clocking crap in. I think that'll work out. So I don't know. Is there there's one called count 16. There's one called count 10. Those might be places to start from. But they're probably for some other weird device. Yeah, see, it's for an ATV750B. I don't know what kind of device that is, and it's very annoying because when you're dealing with this kind of like logic programming language, because this is not Verilog. This is not, no, this pretty much predates all that crap. So you'll see like A9 right here is going to be a pin on the thing, and .T is I assume like the T in flip-flop toggle input for that, and that requires that you have a device that has flip-flops in it that support acting as T flip-flops, assuming that's the T flip-flop toggle input, which I don't think this thing does. So yeah, that's fun. So I'm just gonna go ahead and pretty much delete everything in here. Oh boy. Oh man, I just downed that last little bit of my cup of sangria real fast. Whew. Let me tell you, I'm feeling it. Ooh, this is good to know, is maybe pin node. I was trying to figure out the last time I was working with these is how, if it was possible to like describe internal non-exposed nodes with this, and I don't think it's possible, because it's basically every pin is some combination of logic from the input pins, or, you know, all of the input pins fed through logic array, and then there is a D flip-flop and then the output pin, and that's it. So it's not like you can like feed it back into itself or do more complex routing. It's like, that's what you get. But I was not able to confirm that, but it would be very convenient if you could have buried nodes that aren't directly, you know, representative of pins on the package. Anyway, I don't think that matters for us here. The important thing is, so for the matrix scanning, it should really be as simple as, so how do we design this? Do we put do we do the divide down by 8 on the serial in parallel out gal, or do we do the divide down inside of this thing? And I'm thinking inside of the other gal, but I'm still not quite sure off the top of my head if that is going to actually be possible. So I'm not going to worry about that right now, because we won't even get close to that point in this video, because what we're going to get in this video is I'm going to rip this file apart really quick and just make sure I can write something that is actually compilable for the 16 V8s that I'm using. And I will try and be smart and also resave this file someplace that is not in the examples folder, because that's always what I do, is I just rewrite a file in the examples folder and say F it. But I'll try not to do that this time. So let's just redo these headers really quick. Let's just redo these headers, try and get something compilable that does something, burn it, put it on the board, prove that it actually does something, and go on with our day. So I'm going to call this, let's call this, you know what, actually, you know, it's the easier proof of concept one is the parallel and serial out, because I can just wire that up on the board really quick, and maybe like use the Raspberry Pi Pico that I was just using in the previous stream to drive the clock line in and prove that it clocks crap. So let's call this NES, I don't know, serial in, or maybe shift reg. Let's call it shift reg. And the part number is going to be I believe it's ATF16V8. I can just look at the chat. Let's do that. F16V8B. I think that will work. And it is in fact not the year 2000. Not that this matters, but it is 8, 28, 22. Thrilling. Revision 1, sure. Designer. Let's call me Track 0. Company. Excuse my potty mouth, but we're just gonna call me some fucker. We have no assembly. Why even fill that one out? I'm just gonna delete it. Location. Not even gonna fill it out. I don't care. And then, because I'm dumb. Part number is like the part number of the product that you are making. Whatever. I don't know. Let's just also call it NES shift right. It doesn't really matter. I could delete all of these headers. No one would care. And yeah, so this is literally assigning right here the physical pins on the package to like signal names. And this is the time at which it makes sense for me to pull up the ATF16V8B datasheet. So I can review the actual pins on here. Not like it's complicated, but it's kind of easy to forget. So clock, if you're going to have a clock input, which we will, because that's going to be literally the clock pin coming from the NES for, hey, give me a bit. It's locked to that pin. So if you have clock, it's pin 1. And then these are always inputs, and these can be an input or an output depending on how you wire them up. And I believe also if you use the clock, it also makes this pin always act as output enable, which well, I'll just ground that because I don't need to I don't need to enable and disable my outputs. Let's actually look at the PDIP one. I don't think it differs, but I was not looking at the right package. So yes, clock for pin 1, that makes sense. And then we have 8 pins for input. And so this is fine because going back to this, no, not that. Sure, this. I guess we lost it, but whatever. You can vaguely see on here that there are 8 columns and 1, 2, 3, 4, 5, 6, 6 rows to our keyboard. So what I am planning on doing is I will, like I said, those 6 rows will correspond to this serial in, these wires basically will go into the inputs of our parallel in serial out shift register sort of PLD that we're going to be programming. And I will also have a 7th bit or a 7th bit on there, which is going to be, and I haven't thought this through too much, so we'll see how this works out as I actually have to physically build it. But that's going to be like our sense pin for this is the like 0th column right now or something, so that the NES can know what column it's on and keep track of that, because that's going to be important, because otherwise we would not know what column we're currently on, because we will be, on some arbitrary column when the NES powers on. So I think this works out pretty much perfectly, because if we look at this pinout, we have 8 inputs. We get clock for free. We don't have to think about that. We get 6 inputs for our row inputs from the keyboard. Then our 7th input for that, are we on the 7th thingy input, I guess. And then 8 can be our latch input. Or, 1 can be our latch input or whatever. But I'm going to call this one, because they've kind of already done that work for me. This is similar enough. I'm going to call it latch. Yeah. And that'll kind of work out, because then... yeah, so pin 2 through 7. And let's call this... I'm going to call it row 0. row 0, row 1, row 2, row 3, row 4, and row 5. I'll be up to pin 8. Is there one? Did I do something weird? Pin 1 was clock, and then latch, and then we're gonna have 1, 2, 3, 4, 5, 6. Okay, yes, that makes sense. Right, and then 8, or input 8, pin 9 is going to be our I don't know. Let's call this column sense. Sends. Column sense. And then this pin is ground. Cool. So that's all of the inputs we care about for this type of chip. And I will relabel these as inputs. And then our outputs there's really just going to be one. So we can choose any of these bad boys. Let's call, I don't know, pin 19. We can have be our data out. Can I just call that Q? Is that good enough for me? Do I want to call it data out? Matter of taste. I like slightly more descriptive names. So let's call this D out. And then from here, you literally write, here's the pin, here's the logic that gives that pin a value. And yeah, I believe this is the part where it gets funky, because like I was saying, like with this guy, this .t is for a specific extension that specific device that they were using for this example supports. It's the, again, I think it's the toggle input for a toggle flip-flop. And I think, shoot, I can't remember. I have examples, but they are not on this machine. They are on a machine elsewhere. But, so it's weird and tough because there are two things that we need to do here, right? We need to, for each pin, it needs to basically suck in the value that is on the input pin when latch happens, which is funky. So actually, this gets weird, because our clock is always our clock, but really we want to the values, and we want our D flip-flops inside of this thing to get clocked, which for a D flip-flop means assume the input value, suck it into yourself and remember it during the latch. And then this gets funky if we're gonna use this chip, because we kind of need to we might need to get tricky with the way we're thinking about this, because as far as this kind of PLD is concerned, the clock and latch both kind of act as clocking inputs, because when you latch, like I said, clocks things into the D flip-flop so that they hold on to them, but then when you actually clock to shift things out of the shift register, it requires each D flip-flop. There are 8 D flip-flops in a shift register, and what happens is, the value from this one moves into this one, which its value moves into this one, moves into that one, down the line. That also is a clocking action. So on this kind of PLD, that clock pin literally drives all of the clock inputs on the D flip-flops inside of this chip. You can't assign a different input to the D flip-flop for any given pin. You can't do it. It comes from the clock pin. So we might, firstly, do I even need to latch things? You know what I mean? Because latching, I mean, it is important because it causes us to reset everything, right? The latch is important, especially for resetting the whole keyboard. This is fun because I'm doing design as I'm talking, and it is past 8, so I will probably think through some design, and we're not going to get to building this right this moment. But clearly this will require some thinking through, and we will get back to that next time. But anyway, do I really need to latch things? An immediate thing that occurs to me, and maybe that we will pick up with next time, is we will, the way that I'm building this, every 8 bits that we clock in from the NES, or not every 8, it'll actually be every 7, because we only have 7 inputs here. Every 7 we'll want to cycle the column pin, right, that we are scanning through the keyboard matrix with. And as I was saying earlier, I plan on using that 7th input, that 7th kind of like virtual keyboard row, as our "are we on column 0" like sense line. So ostensibly, if we were using latch to like reset things and know that we are on, you know, clocking in the 0th, or whichever direction, whether it's the first or the last bit of the stuff from the shift register, we can know that, it occurs to me, using that sense line, right? Because we can just power up, and the reset for the keyboard can consist of just keep clocking stuff in until that we're at column 0 sense thing gets hit. Because regardless if it started up at an arbitrary state where it thought it was, you know, like halfway through clocking stuff in from the parallel in serial out shift register thingy that we're building, it will eventually get to the end of that state and move on to the next column. And at some point, you know, as soon as you pull in a value and... Oh, no. See, this is complicated. We're going to have to get back to this next time, because it's not like you're reading all 8 bytes at the same time, or all 7. You're reading them in serial. So you don't know, unless you have reset, which of those bits is the 7th bit, which is the 10th bit. Design, you guys. Design. So, yeah, was really hoping I might get to burn something to this chip, but I hope you have had a fun time with me rambling my design thoughts, because design is funky. You can go in any direction. You can go in any of infinite directions doing any kind of design, much less digital system design, much like this. But I think we've got a rough direction, but we have to figure out this issue of, I want to use these gals, but I only have one available clock input, and latch and clock both kind of do the same thing, or, you know, both require clocking the D flip-flops. So we might just have to play with it. Can it boil down to, and this is where I'm at now, we'll have to see, since that brilliant idea that I was just talking through I talked myself through to, it's not going to work with that sense bit figuring out where we're at based on the sense bit part alone. Can't do it because you don't know where you are in clocking bits in. Anyway, so that means we have to use a latch input in some way to say reset yourself. But, okay, how about this? We can manually control the latch pin from the NES. That's what we can turn it on and off at will at any time. So maybe we'll just have to assert latch and do a clock, and latch will just be used as a logical input to this. That seems more reasonable. Clock will always be our clock. We'll clock even when we latch. Yes. Okay. I hope you followed all of that, because like the last 10 minutes were a blur of thought, but a blur, like I'm thinking that fast. But yeah, I will have to cut it off, but we will resume tomorrow. Same regular schedule, about 5 o'clock EST. I knock off of work and I come right over here to stream. So we will get back to this design question, and we will write the logic here too. Yes, I am pretty sure just have latch as a logical input and always use the clock pin for clocking things is what we're going to have to do. That'll work. Okay, short one, weird one. Thanks for tuning in. Well, relatively short one. It says 50 minutes. Thanks for tuning in for this inauguration of actually building or getting started building some of the hardware for connecting the keyboard to the NES. I will see you tomorrow. And as always, see ya. Love ya.